Yeah, hello everybody. I would like to talk about what I teach in combinatorics. This will be in English because we might have English-speaking students. And yeah, let me start with combinatorics. Combinatorics is a very broad field. So this can be, this includes graph theory, discrepancy theory, discrete geometry, many fields. And so there's no canonical choice of topics. It's not like in universal algebra or like in model theory or like in linear algebra where it's clear that you have to cover certain things, but there's a big freedom for the teacher. And yeah, this can be, so actually one can ask what is the common thing to combinatorics? And one common theme is that, well, what combinatorists like is very simple statements in the sense that you only use elementary words to phrase your problem, but then the solution is very tricky, complicated. It's a complicated proof. And yeah, many case distinctions say, or a priori, it's difficult to predict what tools you're using to solve your problem. Yeah, in linear algebra, all the problems that you could pose, it's clear that usually the tools, they come from linear algebra again to solve your problems. But here in combinatorics, it's hard to predict. The problem dictates the tools. Yeah? And these things together make it actually challenging to teach. Yeah? You have no canonical choice of topics. And proofs with lots of cases are not very attractive for neither the teacher nor the students. So I thought, how can I teach combinatorics? And the approach of this course is to focus on methods, proof methods that can be useful in many different contexts. Also here we have, of course, we have to make a choice of which methods we select. And yeah, of course, I'm biased a little bit, but I have selected 4 chapters, 4 proof methods in combinatorics that I like a lot, that are very useful, like not only for students who plan to work in combinatorics, who want an introduction to combinatorics, but useful tools even if you work in some other fields of discrete mathematics, if you work in model theory, in logic, in theoretical computer science. These are very useful. And the first tool I want to talk about is duality. So there are some, so you might wonder duality. So what first of all, what duality do I mean? I mean duality that comes from linear programming duality, which is an important topic in optimization. So you might be surprised to see it here for combinatorics. But the reason is that many central themes, central results in combinatorics, well-known famous results, like for instance, results about matchings, the Hall's marriage theorem, Koenig's theorem for matchings, min, cut, max flow theorems. They can be seen as special cases of linear programming duality. And they are very similar proofs. There are a lot of cross connections. So I think it's very good to see this theory in this scope of linear programming to put all these things into a common perspective. This is the first method, duality. The second proof method is the probabilistic method. This is a fantastic tool. There's even, if you know this for many years, there's some mystery always remaining about this, the power of this method. So the basic idea is as follows. You want to prove the existence of a certain object with some graph with some crazy properties. For instance, the graph should be not 15 colorable, but at the same time should not have cycles of length at most 42, something like that. Yeah, you would like to have such a graph. How do you construct it? How do you prove that such a thing exists, first of all? And the idea is that you set up a certain probability space, and then you compute in this space the probability that a random object from this space has your property. And if you're able to prove that the probability is strictly larger than 0, you know that such an object must exist. I will say more about all these methods later, but I just want to finish. The third method is Ramsey theory. Ramsey theory is its own hardcore field in combinatorics. Yeah, so it's lots of statements that are very elementary to state, just statements about sets basically and functions between sets, and but very long proofs, very complicated proofs, necessarily complicated proofs. And so first of all, it's a field. So why do I say it's a method? It's a method because it's so often used to prove other things that I think it becomes a method. Yeah, the method is see how to apply Ramsey theory to prove your problem. That's the method. And for this, of course, you have to know the Ramsey's theorem. Ramsey proved a theorem, which is the prototypical Ramsey type theorem. And of course, we'll cover this. And the fourth, a very beautiful topic in combinatorics is generating functions. Generating functions are used in enumerative combinatorics, where you want to count objects of how many objects are there of a certain size. Is again a core topic in combinatorics, that you want to count certain objects. And generating functions make a very nice link, first of all with algebra, power series, and then also with even complex analysis. Yeah, because if you want then to determine the growth of this family, like this counting sequence where you count the number of combinatorial objects, to determine the asymptotics, tools from complex analysis become important. So it links with other things that students in the third year are learning. All right. Okay, so let's go over these four. Duality, I have already mentioned. We have a Koenig's theorem, Hall's marriage theorem, Max-Kadmin flow theorem. These are very beautiful, nice things to teach. And in the course, I will first teach those. And then I will see and I explain how to view them as special cases of linear programming duality. So what's the basic idea? That's not yet linear programming duality. That's an even simpler duality that you already know since your linear algebra course. You have a duality for the satisfiability of linear equation systems. You have a linear equation system, AX equals B, and you would like to know, is it unsatisfiable? So what do? We have all learned this is Gaussian elimination process. You apply Gaussian elimination, and if you can derive an obvious contradiction with Gaussian elimination, if you can derive by row manipulations an equation of the form 0 equals 1, you know there's no solution, and if you can't, you know there is a solution. So you can, this process of finding a proof of unsatisfiability, you can formulate it itself as a linear equation system, a certain linear equation system. So you get unsatisfiability if and only if some other system, which is the dual, has a solution. Because a solution to this other system is a proof of unsatisfiability. It is an instruction of how to combine the rows of your equation system into an unsatisfiable equation, which proves unsatisfiability. So this is one of those dualities. And this can be now generalized in 2 steps. It can be generalized to linear inequalities. So you have a corresponding theorem for linear inequalities. And then you even have a generalization in the next step to minimization problems or maximization, linear minimization or linear maximization problems. And that's the duality then that has so many applications in combinatorics. All right, so that's the method. And what are the topics? So in this chapter, I will start with some basics about graphs. Then in each of these chapters, I have some en passant common knowledge that is not part of the chapter really, but I also teach to put things into context, which is in this chapter, some basics about complexity theory, because there are important applications of linear programming duality in theoretical computer science. Then I will start slowly with these very intuitive and nice theorems of Hall and Koenig. I will teach LP duality. I also teach it with proof. Yeah, so we will prove it. This is based on Motzkin elimination, the simplest proof I know. It's not difficult. And then we'll apply it. Yeah, so you might wonder, are these linear inequalities? They are over the reals. So why does this help? Solutions over the reals, why do they help me in combinatorics? Yeah, and that's not always clear, but there are some conditions that tell me if there is a solution, there is also a solution with integers. Yeah, and this helps me then in combinatorics. So there's another topic. And then we have 3 applications of the theory. We'll look at network flows. We'll prove the Neumann minimax theorem in game theory. And there's also some applications for simple stochastic games. And there is a very nice book for reading more. It's for undergraduates. It's very nicely written, very detailed, very intuitive, by Matuszek and Gärtner, which is sort of the background text for this chapter. All right, then we have the probabilistic method. Yeah, I already told you, this is the goal here is to show that certain objects exist. I have already outlined you this. Define the right probability space, prove that a random object from this probability space has the property with positive probability, then such a property must exist. Sometimes it's even the case that the objects, the random objects, have the property with high probability, with probability tending towards 1. Then sometimes the computations just come out like that. So, but it's enough to prove that the probability is larger than 0 to know that such an object must exist. And it's really curious, and that's what I meant by mystery, that sometimes the only known proofs are of this type. There is no deterministic proof which would really show the object. You only know that the object exists, but you have no clue how it looks like. And so to really go to so what's the topics that I'll teach there, to really go, focus on this mystery, I have investigated what's the simplest type of statement where such a phenomenon happens, where we only have a probabilistic proof. And this is a very simple statement about the existence of so-called K-paradoxical tournaments. There's a hyper short proof that's probabilistic, and we don't have an explicit proof. So that will be the first topic in this chapter. And then the other highlight in this chapter is that I want to prove these graphs that have no short cycles and still have high chromatic number. That's a very famous result by Adesh. We want to prove that. Here, the situation is more tricky. We just can't take the uniform distribution on graphs of size n. This is this graph model GNP. So, but we GN1/2. Every edge is present with the same probability 1/2 independently. But this probability space needs to be chosen more cleverly in the sense that this probability P for an edge to be there or not needs to be chosen from a specific range as a function depending on n in order to make this probabilistic proof work. And so what I do next in this chapter is that I'll explain how GNP, like random graphs with edge probability P with n vertices, how they evolve if you increase the edge probability. Now, this is called the Erdős-Rényi evolution. And it's very beautiful because you can discuss what happens if the edge probability is a little bit higher. How do the graphs look with high probability asymptotically, almost surely? And this is... and then there are 2 very important methods in the probabilistic method. It's the first moment method that works with expectations and the second moment method. And that's it. That's the second chapter. Third chapter is Ramsey theory. The philosophy there is complete disorder is impossible. This is maybe a little bit cryptic. Another theme there is the statement, how large must a structure be so that a particular property holds? That captures many Ramsey statements, not all of them maybe. So to make it more concrete, yeah, what do I mean? If I, now this is like a baby Ramsey statement. If I partition an infinite set into a finite number of pieces, one of the pieces must be infinite. It's the infinite pigeonhole principle. This can be seen as the first theorem that fits to this second theme, how large must the structure be so that a particular property holds. Another like concrete Ramsey type statement is that if you have an infinite graph It must either contain an infinite clique where every vertex is connected with every other vertex, or an infinite independent set where no vertex is connected to no other vertex. These are typical examples of Ramsey statements and special cases of Ramsey's theorem. So what will we prove here? We'll prove Ramsey's theorem. There's important cross connections with the probabilistic method, because to construct lower bounds for Ramsey type statements, you need very often probabilistic methods. And then I present these various applications. There are lots of applications, and I've selected 3, one from number theory, one from discrete geometry, and one from, well, positional games, where you learn how to see how to apply these Ramsey statements. All right. And then there is the 4th chapter, generating functions. How many objects of a certain size are there? For example, how many graphs are there with vertices 1 up to n? This is a so-called labeled enumeration problem. Labeled because the vertices are labeled with 1 up to n. And this gives you a function, integer valued function, defined on the natural numbers that counts. Then there's always in combinatorics, in enumerative combinatorics, usually an unlabeled version where we are interested in the number of graphs with n vertices up to isomorphism. There's another counting function. And there's some interesting connections between the labeled and the unlabeled counting. And then we can count various things. We can count the number of equivalence relations, or we can count the number of words over the alphabet A, B, C, and so on, which contain the word algebra, but not the word analysis. How many are there? No? How do we approach this? And in general, this of course can be very difficult, but very, very often generating functions are extremely useful here. And so suppose we are, and first of all, what are we interested in? We are interested in, as a result, maybe an elegant formula. Maybe the formula is not elegant, but still it can be computed efficiently. That's another nice thing that we can look for algorithms to compute the number. We might also be interested in the asymptotic growth. How quickly does it grow? This is important if you want to estimate or lower and upper bounds. Yeah, and for all these, there's as a first step, a tool, power series, and as a second step, generating functions. So what's the idea? Suppose you have some sequence of numbers that count something. And very often, if you count something, because you can decompose the things that you count, you have maybe these numbers are given by a recursion. Like here, for instance, in my example, the recursion is given an plus 1 is, say, 2an plus 1. Okay, and we start with 0. And we would like to have these other items that I asked for, asymptotic growth. How can we compute these numbers? Do we have maybe a more elegant formula for it? And the first step is, this is almost like a recipe. We first define the following formal object. We turn this into a power series where the coefficients are the numbers that we are interested in. And we have this formal variable x, and x to the n labels the nth number. Okay, and now we can view this as a power series and can perform algebraic manipulations. And in this concrete example, it comes out, it just so happens that by this algebraic, you can write this formal power series as a fraction of 2 polynomials. And from this fraction, you can then extract the coefficients back, and you get that this nice formula, an is 2 to the n minus 1. In this simple example, there would have been a direct proof, I admit it, but it's just a toy example. This recipe, you can apply it now to your favorite sequence of numbers that count something. And there's a nice book, again written for undergraduates, maybe, well, it's maybe a little bit fast for undergraduates, but it's a very famous book. It's freely available. It's called Generating Functionology. That focuses on this part of the theory. The book is a little bit short on the second part of generating functions, which is the second part of this chapter. And the idea here is that now you have this power series, and for certain, say, complex numbers, this power series might converge. If you replace x by this complex number, you get out a value. So so you can go from power series to analytic functions if in the radius of convergence, and you can go by Taylor expansion, you can go back. And this going back and forth is very powerful, in particular if you are interested in the asymptotic growth of the numbers you're interested in. Because the radius, it's very closely linked to the radius of convergence of this analytic function. And I should say, when I say radius of convergence, it's important to note that there are two settings in which we can, I have already mentioned labeled enumeration and unlabeled enumeration. For certain enumeration problems, the radius of convergence will be 0. And then this method is boring. So very often in this setting, we work with the exponential generating function. This happens for labeled enumeration problems where we have a little n factorial in the denominator. And then the radius of convergence is, it tells you a lot about asymptotic growth. All right, so this is to give you some idea. And again, topics where we will apply this is like the Fibonacci numbers. We will look at regular languages, like for instance, the language of all words that contain algebra, but not analysis. Dissections of convex n-gons, which are counted by the Catalan numbers. Partitions, very important sequence of numbers. Two regular graphs, we look at permutations, connected graphs, labeled trees. These are things that we will then be able to count and get nice formulas and lots of cross connections. Okay, some high-level comments before I finish. So this is a 3+1 course, meaning that we have 3 sessions that are lecture. I plan to lecture at the Blackboard. Hopefully this is again possible. And one session every 2 weeks is then exercises, where there will be exercises given out, and in these sessions we'll discuss the solutions. The target audience is bachelor students in their 3rd year. And there are also computer science students with a minor in mathematics. I taught this course once before. And from this, there is an English course notes. They are publicly available on the web. And the course is in English on demand. Otherwise, we can discuss. I mean, the course notes, I'll not translate them, but the teaching could be in German. Then. I also once used this as a source of topics for a seminar where students picked out some subchapter or subsection from these course notes and elaborated a little bit. This also worked quite well, I found. And what did I want to say? If you want to have a look at this course notes and you find some places unclear, typos, obviously you can send them. You can send me an email. I'm always happy. But also if you think in combinatorics you should teach this and that, I'm happy to receive emails about suggestions. Yeah, and I think this is my last slide, and I'm happy to answer questions.